Okay, sorry about the delayed start, everybody. Welcome to week 3 of Robot Systems Programming, Spring 2018. I've updated the course webpage pretty significantly, and you can take a look at it. This week's module is going to be to assemble and do some basic development with the EduMIP. What we're going to do today in class, after some organizational stuff, is I'm going to just review the steps on assembling the EduMIPs, burning images and things like that. The things that, looking forward, the thing that I've added to the course webpage down here is item number 17. What I expect to happen for the course moving forward, we're in week 3, module 3, EduMIPs. Next week, you're going to learn how to use RViz, and you're going to write an URDEF, Universal Robot Description Format file, which will tell RViz how to display the shape of the EduMIP, and you're going to write some code in order to broadcast the appropriate frames so that RViz can display the robot in real time, and you're going to you're going to inform that display by data that comes out of the real robot. So as you drive your robot around on the floor in your apartment, then it'll also be driving around the floor in RViz. It's up to you as to whether you want to introduce a model of your apartment into RViz. Next week, we're going to then add physics to the URDEF, and that's called an SDF. And we're going to then run this physics simulation of the EduMIP in a physics engine called Gazebo, and you'll be able to drag it around. And we'll actually then the next week, I'll give you a plugin, and what the plugin will do is it'll provide a control system which will balance the robot. And so you'll have a simulated robot in Gazebo that you can drive around with the same joystick, and it produces the same output stream of information that the actual hardware does. And so I want you to really get the experience of doing physics-based simulation. And things like if you kill the control program that's running in the simulation, the robot will fall down. So all those things happen. Week 7, you're going to do some simulation in Gazebo with a Turtlebot 2 simulated Turtlebot 2, driving around in an environment. It's a 2-part laboratory. In the first part, you're going to drive the Turtlebot around in an environment with some obstacles and objects, and you're going to use a package called GMapping, which is a SLAM package, simultaneous localization and mapping. And if you've taken Simon Leonard's course, you know what that is. And you can drive around in the environment, and you're going to generate a 2D map, an occupancy grid of this world. Then once you think you've got a decent enough map for driving around, you save it. And then you're going to load up a different package running the same Turtlebot, and it's called Adaptive Monte Carlo Localization. And it does a particle filter estimation on where the vehicle is. And we'll talk more about it then. But it's the point of this simulation is that these are sort of adult varsity packages for doing SLAM navigation and adaptive Monte Carlo localization. And in this course, I don't teach those algorithms. I'm counting on you to have algorithms for sensor-based robotics to introduce you to these kinds of things. And but in this course, I want you to get some time on actually using them. Then there's spring break, week of March 20th. And then after spring break, I'm trying to decide, I may make this module 8, the week after spring break optional, and just an extra credit thing. So depending on whether this week 8 is required or extra credit, then we'll have either 5 or 6 weeks of an independent project. The rest of the semester is independent project. And so what we'll do is during week 1, I want you to get together with a potential team, and we may have some sort of speed dating between now and then, so students can meet each other and talk about different ideas. The idea is to get together with a team of ideally up to 3 students. If you're super antisocial like me, you can work in a team of 1. But I urge you actually to work with a partner, because I find that if you work with somebody, you learn from them. So in week 1, you need to plan a project and write a project proposal. And clearly there's some things that I need to fix on this thing, assignments. The date is from last year, so I'll fix that. And the project proposal is going to, there's an outline here of what the project proposal is, member names, what is the system going to do, what kind of hardware do you need, what kind of software do you need, what part of that hardware is stuff that we already have around that you've identified, either that I have for this course, or maybe your advisor has in her laboratory. What software will need to be developed, and what existing software can you use? So sort of an outline of the project. If it's more than, I want you to address a safety plan, and then I want you to have sort of a schedule of work to do the project. And there's some notes here about sort of project-oriented notes. And then basically for the rest of the semester, the class will basically be primarily clinic, but we'll have some supplementary topics each week, like how do you use a GPS, how does namespacing work, a whole bunch of different things that are more advanced topics that are not going to be formal assignments that you'll have to hand in, but they're things that you're going to know, because if you're using more than one robot in your project, you need to understand namespaces. And so we'll have one or two topics every week as sort of supplementary topics. And then, excuse me, there's no final exam in this course, but at the date that we would have had the final exam, if there were one, we'll have a poster session. So 9 a.m. to 12 a.m., Saturday, May 12th, mark your calendar. We'll have a poster session in Hackerman Hall, and we'll set up a Wi-Fi, a Turtlebot Wi-Fi network in Hackerman, and so great if you could actually demonstrate your project, actually physically in Hackerman. If your project requires physical affordances that aren't available in Hackerman, then it's okay to have a poster, and if you have a video, that'd be great too. So that's the idea. So we'll have 7 or 8 weeks of programmed assignments followed by independent project. Any questions on where we're going? Yes?
Throughout the semester, are you going to start introducing the possible projects?
Yes. Yep. In fact, we're going to, let's look at a few now. YouTube video course presentations. So if you, I think what I should do is I should probably post for you to look at the posters from last year's projects, so you can sort of browse through the posters. So I'll do that. And I'm going to post a big PDF of the posters from last year as a multi-page PDF, so you can scan through it. And if you go to YouTube and you search for 53707, one too many zeros. Sorry. YouTube. And you search for 53707. So this is that's the channel for the recorded lectures from this spring. And right now we've got 4 lectures, 8 views, 4 views, so it looks like it's not being terribly useful, but it's an experiment. That's fine. Spring 2017, these are some videos from last year's. So if you click on videos here, you'll see a bunch of videos from last year's projects, and I think I played a few of these. On the first day of class, the projectors are working a little bit better. Let's see. I totally forgot. I wrote it on the board, though. Tyler Payne has offered to host additional office hours 1 p.m. Tomorrow, Valentine's Day. He said that chocolate was not required, but it'd be appreciated. And his office is in Krieger 70, the Hydro Lab. The door to the Hydro Lab is in that passageway if you're going from the old engineering quad over to the library. If the doors aren't open, then you can just call him on the laboratory phone and he'll come get you. And we want to be available if you need help soldering your kit. And if you can't make that time and you need help soldering some other time, then give me or Tyler a call and we'll help you out. For example, we have 6 UR5 arms, and Nicole Ortega and Kevin Yim did this project last year, where they had a 4K camera looking down from overhead, and they made a bunch of chess pieces out of foam core, and they put AR tags in each of them, and they calibrated the robot to the camera, did hand-eye calibration, and then they used an open source chess playing program, and when the human would move the chess player, it would recognize that the human had made the move. It would run the open source chess playing program, and it would then move the robot's pieces. And it did not just basic playing, but it did the sort of the other moves like castling and capturing things. There are these odd moves that are available in chess, and it did all of those things. It was pretty impressive, actually. On the course webpage, there is a list, which I will augment, of resources that are available to you. These are the previous year's course webpage, 2016, going back. Let's see. Sorry, that link is not working. I'll have to find out what's wrong with that. This is my old website. So resources that we have available. We have 6 UR5s over in the teaching lab. And I think all of you have already used them. We have EduMIPs, and we have extra EduMIPs. So if you want to make an EduMIP army and swarm with them, you can. We have 5 Turtlebot 2s, and that's a little robot about this big with a PC on it and a laptop, and it's got a odometer, compass, and it has a Kinect, so RGB and depth sensor. And you'll become familiar with the Turtlebot in the week 7 assignment. You'll work with it in simulation. We've got a bunch of Parrot AR drones, and we have a place to fly them over in the lab. I think I already showed this video from last year. So Ryan, Lydia, and Nick did this project. So this is we have a place to fly the drones over in the Hydro Lab. It measures, it's not as big as I'd like. It's 10 feet wide, it's 20 feet long, and 16 feet high. It's a little bit too narrow. And the thing that we found with these AR drones is they're pretty cheap. They're like $300, but they're you can only use the downward-looking camera or the forward-looking camera at once. You can't use them both, and switching between them is not very convenient. So if your heart set is on doing a drone project, I think we might want to think about doing a little bit of research and getting a better drone. Spending a little bit more money and getting something that is a little more capable. These are good and inexpensive, so if you crash them, then it's not a big disaster. And what they did was they had the drone hovering above, navigating itself with respect to AR tags, and I wanted them to have the drone search around for the robot on the ground, and land on it or do something like that. But they were dug in. They really wanted to have the drone hovering in the sky, and then the robot searching around for it, finding it, and then sending a command to land. And they got it working. It was pretty impressive. They put in some late nights. And so there's the TurtleBot right there.
Hello, Coach Dad here, and I'm going to show you how to move the pieces of chess. And if you look at it all, it can be very complicated with all these pieces. There's 16 pieces on each side.
So that's another project. Other resources that we have, we've got two open ROV underwater robots, and let me see if I can find the videos for that. Yeah, Sharyar and Laughlin. They took an open ROV small underwater robot, and let me show you what that is. So this is a small robot about this big, about yay big. It's got one vertical thruster and two horizontal thrusters, and it's passively stable in roll and pitch. These are the batteries. It's got a camera here, kind of a crappy camera. And what Laughlin and Sharyar did was they built up one of these things from a kit, and we've since built up a second one. And they took the crappy camera that comes with the robot and replaced it temporarily with a decent machine vision camera. And they also put in this robot runs on a BeagleBone Black, and so they put in a second BeagleBone Black that just for image processing. And both of these of the BeagleBones in this pressure housing could talk Ethernet up the power line to the surface. There's a power over Ethernet 2-wire interface, and they. So what you can see here is this is a view of the tank, and they're firing things up on the console of a computer. That's the robot right there, the surface floating. And these are the walls of the water tank that we have over in the Hydro Lab. It's about 8 meters in diameter and about 4.5 meters deep. It's 195 cubic meters. And so this is opening up the console. And they built a ROS interface to the OpenROV software. So they could read as ROS topics the status of the machine, and they could command things like forward thrust. And in this demo, the robot is being flown around the water tank with a joystick. And you'll see it's using a forward-looking visual odometry package. And in RViz, you'll see and it's doing visual odometry based upon features in the environment. And so you'll see what's going on in the actual tank over here in this window, the video window, and what the robot software knows. So that's the view out of the robot camera, looking at the inside wall of the tank. On the floor is carpet that's held down with bricks. And that's feature detection. And these are feature detections in the real-time image from the vehicle camera. And it just went away, but on the left in RViz, because RViz crashes, you can see the features being displayed in three-dimensional space. And so they flew the robot around in this demonstration. They're flying the robot around the space, and the three-dimensional odometry is building up a set of points which represent the shape of the tank, and it's simultaneously estimating the vehicle position with respect to those targets. So eventually, in this video, the RViz starts running properly. There we go. And so we can see the views out of the cameras on the vehicle, and I think there are 2 cameras in the vehicle. And as they drive around the tank, you can see that it builds up a growing dot cloud, and there you can basically see the tank, and there's the track of the vehicle within the tank. So it was a pretty impressive project that they did. So all visual odometry. Okay, so I'll show a few more every class, but I want you to start thinking about this. So we've got 2 underwater robots. We've got 2 RC cars that have been converted to have an i7 processor on them with a laser scanner. So there's computer control of the RC car, and we've got some students who are pretty expert at it to help advise the project. Yeah, and these are all the different parts that we bought to build up the cars. There's sources for additional sensors and actuators here, and we have a spreadsheet of sensors and actuators that we already have in inventory here. So if you want to try something out, we've got a whole bunch of servos and different sensors and actuators that we have available. So if you want to prototype something up to evaluate the feasibility of a project. So I wanted to get you thinking about the project. So I don't want you to start thinking about it the week after spring break. I want you to start thinking about it now. Any questions? Okay, then let's get going. So week 3. Oh, right. So robot of the day. So we looked at Big Dog last time and saw a video that was from 10 years ago. And so the company that built it is Boston Dynamics, which is headed by Mark Rabert, and was acquired not too long ago by Google. And the chief engineer is my graduate school friend and lab mate Al Rizzi, and what they've done in this last 10 years is many things, but in particular they've moved from internal combustion engine power to battery power. So they've really improved their actuation and energy efficiency by orders of magnitude. And they've also they built a large electric vehicle that you can look at called Spot, and then more recently Spot Mini. So I thought I'd show a few videos of Spot Mini. This was the introductory video, just a teaser. But it looks bigger here than it really is. And notice that with the articulation of the legs, it's a lot less creepy. But there are some creepy things about it. So this is Spot right here, and this is Spot Mini. And you can see they both have laser scanners on their head. And you can get a sense of Spot Mini's size with respect to your average Boston Dynamics engineer. And that thing on the top of Spot Mini is a little articulated arm with a gripper on the end of it, which I find truly creepy. First time I saw it, I was like, ick! I don't want to remember that. I'll have nightmares. And this is all being teleoperated, but I think it's just a stunning technical achievement because I say teleoperated, but for example, if you want to drive the vehicle forward, you just push the joystick forward. You don't tell it where to place its feet. You don't tell it when to pick up the feet. You don't tell it what gate to use, and it can get up. And so it's planning its planning system is planning where the feet land and the stance for that kind of thing. So. This is in the sort of Star Wars droid look. So, a lot happened in 10 years, and the Boston Dynamic folks have been busy. So, anyways, you can peruse that more. All right, so EduMIPS. Let's do EduMIPS. Any questions on organization of the course and where we're going? Okay. I'm going to basically briefly review assembling the EduMIP. About half of you have pre-assembled EduMIPs, and about a little more than half of you have to assemble a kit. We're going to assemble the EduMIP. You're going to bring up Linux on it. You're going to log into it, and you're going to write some packages. So I want you to read about the ROS Joy package. I want you to read about ROS timers. A timer. So the ROS Joy package is a node that you run that reads a joystick and publishes it as a Joy topic. And I want you to read these examples on timer callbacks. And what a timer callback is useful for is in a ROS node, sometimes you want to do things periodically. And if it's something you want to do periodically and it's going to take a very short period of time, and you want it to happen, say, at 1 hertz exactly or 10 hertz, a timer callback is the appropriate thing. And you'll create a timer callback here with, for example, this creates a timer callback which with duration is 100 milliseconds, tenth of a second, and it calls the, excuse me, it'll generate a timer event, and it'll call this callback function every 100 milliseconds. For example, in the code that I'll show you in a little bit, we know that the joystick generates joy messages only when you move the stick. It doesn't generate them continuously. And so in my sample node that I did, which is the same thing that you're going to be doing, I chose to subscribe to the joy topic, but then I generated commands to the robot at, I don't remember what it was like 100 milliseconds regularly. So it would generate a continuous stream of commands because the robot has a dead man timeout that if you don't send it commands for, I think it's 2 seconds, then it'll stop. So we'll look at that, read about the documentation about timer callbacks, and I'll give an example later on in this class. Read the documentation on running ROS across multiple machines, and I'll demonstrate that today during class. And you can read the documentation on the joy message type and the twist message type. Joy is part of the sensor message types, and twist message is part of the geometry messages. And so has anybody assembled their EduMIP already? Curious. No? Okay. All right. So first task is to assemble your EduMIP and bring it up. And that's documented on this separate page. So ROS and the EduMIP. Introduction, a little bit about EduMIP origin story here. My friend Tom Bewley invented them as part of his undergraduate control systems course. The list of ingredients, you need a BeagleBone Blue or a BeagleBone Black with a robotics cape, because the functionality of these two things were squeezed together onto this one board. And all the kits that we have, the new kits, are all BeagleBone Blues. And the BeagleBone Blue or the robotics cape both have the same instrumentation. They've got a 9-axis IMU. It's got 3 accelerometers, 3 angular rate gyros, 3 magnetometers, temperature sensor. It's got a pressure sensor, barometer, pressure sensor. It's got 4. Hang on a second. Got to wait for it to process my... Oh, wrong camera. Too dark. Oh, wait. This is the right camera. There you go. So here's my machine, and a little bit blinded by the light. So this is BeagleBone Black. The BeagleBone Blue looks a little bit different. So the blue is on the left here, the black is on the right, and you can see the blue consists of a single board with all the functionality on one board. The black consists of two boards. There's a main CPU board down here, and then there's the so-called robotics cape here, and they connect through these lines of pins over here. But they're very similar in their configuration. This is the bottom near the wheel. What we have here is we've got 4 encoder inputs right here for encoders, and you can see 2 of the encoder inputs are connected to the encoders for these wheels right here. Those are the encoder right there, and these are the encoder inputs. And if you have your BeagleBone Blue or your black here, you can take a look at it and you can see these. And these are 4, and the encoder connections have 4 pins for power, ground, channel 1 and channel 2. And these are the servo output pins, and so these do PWM output at the battery pack voltage level, so they'll drive motors directly, so they've got a plus and a minus, and there's 4 of them. And that's what's driving the servos on the EduMIP. And the motors are inside here with a gearbox. And here's a motor. You can see a motor there, a gearbox, and then the encoder off to the right. Continuing on the sort of garden tour, these are 8 3-wire connections for 8 radio-controlled airplane servos, so they can drive 8 servos directly. And up here, we've got a USB for USB client devices. So if you want to add extra devices that are USB based, then that's a USB master. You'll connect the first time to the board through this USB connection, USB micro connection, and this is running a DHCP Ethernet server on this port. And so that's the way you'll connect to it for the first time. For the BeagleBone Blue, there's one 12-volt connection to it for charging, and there's circuitry right here that we're being blinded by that'll charge the lithium polymer battery pack here. So one of the really nice things about this is that most embedded boards that you get have some kind of a processor and various sorts of I/O, but then you're like, oh, I need to power this thing. And you have to have this entire separate battery subsystem. Well, in this case, the battery subsystem is built on board. There's 4 user switches that you can use for various things. Right now, if you press the power switch, it's running a little daemon. It'll power down the machine. And this is the CPU and memory here in a module. And this is the Wi-Fi and Bluetooth driver. The whiskers are the Wi-Fi antennas. And over here are a bunch of connectors that support serial input, serial output, analog output, SPI and I2C, which is a 1 or 2 wire serial interface for interfacing to external devices, so it's very I/O rich. And on the back of the board is physically the IMU and the pressure sensor, and all the same things are here on the BeagleBone Black robotics cape. This is the older design where everything is built on a daughter board, but it's got the same capabilities. And the one thing that I want to warn you is if you look at the older system, if you've got a pre-assembled one, there's 2 connectors for charging. This one that's plugged up down here is for 5-volt only charging, and if you plug your 9 or 12-volt adapter into it, then you'll smoke the board. And so up here is, unfortunately, very unfortunately, with the exact same size connector, this will accept, I think it's 6 to 16 volts. And the adapters that I have for you are 9-volt adapters for charging. So a good thing to do, in case I forget to say later, hopefully I'll remember when we're up and running, is when you're done using your BeagleBone for a session and you're about to put it back in its house and carry it around in your backpack, it's a good thing to power down the CPU with the command sudo power off. It'll ask for the sudo password, and then it'll power itself down. And then unplug this battery connection here. And that way, if you unplug the battery connection, when it's rattling around in your backpack and in the plastic case, if some piece of metal shorts out connections on the board, then it won't smoke the board. And then when you want to boot the thing back up, just plug in the battery connection and it'll boot right up. Sorry if you're getting seasick with this. Any questions about the physical infrastructure? Okay. We also gave you an EduMip kit, which has the bits and pieces, and a microSD card. I think there were 16 gigabyte ones for the new one. And at this link, I've posted 2 images for Linux, and I've also posted instructions on how to build the EduMip. So I want you to download these instructions, and you're going to download one of these 2 images. Do it while you're on campus because they're 2.5 gigabytes. One image is for the BeagleBone Black Wireless, and one is for the BeagleBone Blue. They're zipped. The unzipped size is about 8 gigabytes, but you don't need to unzip them because the image burner will do that for you. And let's see, and you need a USB joystick. So first things first, we need to assemble. And so there's 2 parts here. One is assembling the EduMip with a BeagleBone Blue and Robotics Cape, and everybody here who has a new kit, it's with the BeagleBone Blue. The inventory of the kit is about the same. These are the kit parts. If you have a BeagleBone Blue, then you just have 1 board here, not 2 boards. You can see once you disassemble the carrier for the motors, you can see the gearboxes here, and the motor carrier and the wheels. The kit is short on some screws, and we have extra screws, and I believe that Tyler and Soham already added extra screws to your kit. If you are short on any screws, just see them. We have them in inventory. Your kit has a connectorized wire for connecting the encoders. One end goes to the encoder, one end goes to the board, and then it has a whip wire with one end as a connector that plugs into the CPU, and these 2 wires get soldered onto the motor tabs. And the motor tabs are labeled plus and minus, and red is plus and black is minus. And this shows, this is an older photo from an earlier version where there were no connectors on the encoder boards. Your encoder boards have connectors, so that's not appropriate. And then assembly, we want to fast forward to the BeagleBone Blue assembly. That's what an assembled BeagleBone Blue looks like. We're just looking at one. It says that you're going to need to mod the part by breaking off this little tab. Tyler and Soham already did that for you. They already did the mod. Problem is that when they built the BeagleBone Blue, they put one of the sensors right here, and it interfered with that tab, but it's not really required. The lower front bumper on the BeagleBone here, right here, it protects these wires, and it went between the boards on the old design where there was 2 boards. On this design where there's just 1 board, what we've done is we've drilled out the hole here, so this hole is now a clearance hole, and you use a half-inch number 4 self-threading screw to screw this in. And so the instructions say that for that bumper, that you need to, the lower front bumper needs to be modified by drilling out its 2 threaded holes with a 1/8 inch drill. We've already done that. So your kid has already had that done to it. And you'll need to find a pair of number 4 by 1/2 inch. Number 4 is the thread diameter, 1/2 inches is the thread length, not including the head. The instructions, if you look on the Strawson web page, they identify the screws as a 440, which is not true. That's a machine screw. But it was written by a computer scientist, so what do you expect? And so your kit has already been drilled out with these 2 holes for the lower bumper. And this sort of shows how I assembled the BeagleBone Blue with a single board. And what you can see here is this is the top bumper or horns that catch the robot when it falls forward and backward. So these upper horns, their purpose is so when the robot falls down, it doesn't whap any of this electronics. And the lower bumper is so that when it falls down on top of something, it doesn't whack any of this electronics, whatever it falls on. And so this is a plastic carrier which captures the battery. And the way I've done it is that I used a 3/8 inch number 4, and I screwed through this clearance hole, and the screw is actually threaded into this plastic here. And to hold the BeagleBone Blue to the base, you can see, just barely see that there's a screw that's threaded. I guess you can't see it. I think it's on a different, yeah. And the way the BeagleBone Blue is attached to the base is with these 2 screws right here. So they go through a clearance hole that's in the board, and they thread into the base. And these horns look like they're there magically because they're being held in by a screw that comes from the back. So I tried to make enough pictures here that you can see where things are, what is screwed to what. And when in doubt, see me or a TA. So once you've physically assembled the BeagleBone, then you can charge it up. The batteries usually ship with about somewhere between a half and a third charge. It doesn't take very long to charge up, and when you get all 4 lights showing on the little charging thing here, you know you're charged up. And when you plug it in, if it needs to charge, these charge lights will be doing this sort of crawly thing, where they're going, 1, 2, 3, 4 lights, 1, 2, 3, 4 lights. And once it's fully charged, then it will be solid 4 green lights. I'm always careful with lithium-ion batteries, and so it doesn't take very long to charge these things. They charge to a full charge in an hour, 2 hours tops. And so just as a matter of precaution, we haven't had any problem with these things, and I think it's a good design, but I wouldn't plug this thing in and leave it at home unattended overnight, or with my roommate, or in my case, my wife, just because lithium batteries can cook off, and the electronics on these things gets beat up all the time. And so my recommendation with lithium batteries of this sort is to charge it while you're around. And if you're going to be going away and leaving it, then stop the charging, and that way you're guaranteed to be safe. We haven't had any incidents whatsoever, but I always exercise an abundance of caution with lithium batteries. Okay, so assembling the EduMIP, and there's a video here which is pretty instructive. And this video is for assembling with the BeagleBone Blue. So I already cautioned you about don't plug the 9-volt charger into the 5-volt connector if you have one of the older style things. Unplug when not in use, and disconnect the battery from the motherboard. Don't just throw it in your backpack. Throw it in the Tupperware, and throw the Tupperware in your backpack. The motor and encoder connectors are a little bit delicate, so just be careful with them. And if your encoder starts falling apart, then stop by and see me or one of the TAs, and we have a hot glue gun and we can glue it back together. So these instructions apply for both BeagleBone Blue and BeagleBone Black. The first thing that you want to do when you get your board is you want to take the micro USB to USB-A connection and you want to plug it in to the micro USB connector here. So when you first bring it up, this thing won't have connected to your Wi-Fi network, and so you're going to need to get into it and talk to it at all. And the way you'll do that is this says BeagleBone Blue, but it holds for anything. And let me just log in here. So I'm going to shut this thing down, and that's not the one I wanted to shut down. I'm going to shut down this BeagleBone Blue, and I'm going to do that by hitting the power button, if I can read it. And it's going to go through its shutdown sequence, and it'll have just one light left, so it's shut down. And I'm going to pop out the microSD card, and then we're going to. So this thing comes with an internal 4 gigabyte Debian image burned onto it, and so the first thing you want to do is to just boot it up with its internal Debian image, and do that by plugging in the battery. And when you plug in the battery, the thing will boot up. And then connect the micro USB to USB port on your computer. And do I have any spare USBs? Yes. And so it comes up, it's booted out of its own internal image, the default image that comes from the factory. And so I'm looking at my host PC here, and ifconfig gives me my my network configuration. This is my wired Ethernet connection. This is my wireless Ethernet connection, and this is the so-called loopback connection, which is used for when programs are communicating. Two programs on the same machine are communicating to each other. So when I plug the USB port into this thing, having followed the instructions, then I'm going to see some additional connections pop up, and the additional connections are 192.168.7.1, and this is the name of the Ethernet adapter. So what's going on is the BeagleBone Blue is running a DHCP server, and it's serving Ethernet over this port, and my machine has just gotten a DHCP address to it, and my machine is 192.168.7.1, and the address of this thing over the USB is 192.168.7.2. So if I ping 192.168.7.2, there's something out there. That's the DHCP server, and if I SSH to Debian at 192.168.70.2. And then it'll say, are you sure? Yes. And the password for the Debian login is temp. So the whole point here is just to verify that your BeagleBone Blue runs at all. If you DF, you'll see that it's got a half a gig of RAM. It's got 4 gigs of flash, and it's running a relatively recent version of Debian. This is also actually running Apache, and if we web browse to 192.168.7.2, Patrick gets around to it, it's serving this web page, which has all the documentation on it. So it's kind of cute. So going back to the instructions, so assemble. So instructions here. So the first thing to do is to see whether you can talk to the board and connect to it. And once you verify that your board is working properly, then you can shut it down. And I will shut it down by doing, we're logged in as Debian, so I'll do a sudo power off, temp password. And then I'll unplug the battery, and that's it. Next, we want to burn an image, and so choose the appropriate image from the Dropbox here, download it, and the way we'll burn the image is, let me get a SD card. So here's a microSD card. This one, it happens to be 16 gigabytes. And my PC has an SD card slot, and so we gave you microSD cards and microSD to SD adapters because a lot of computers have them. If your PC does not have a microSD or an SD slot, then the TAs have 10 USB devices for burning cards, and you're welcome to borrow one. So when I put this into my computer, I believe that there's a formatted image on this. And so it pops up, and let's see, this particular random card that I pulled out of my backpack, it has two partitions on it, boot and root file system, and I'm going to unmount them because we want to burn a new image onto this thing, and it's going to burn it into a single partition. And and I've asked you to so download the appropriate image. Where are we? Here we are. Download the appropriate image and download Etcher from this website. And you can use a different burning program if you want, but I find Etcher to be pretty convenient. There, and so Etcher comes up here. Skip. I want to select the image that I want to burn, and so on my computer that's here, code, BeagleBone Black, Ubuntu, and I'm going to burn this image. It's the BeagleBone Blue 6.04 Ubuntu LTS edgymip ROS image.zip, and I'm selecting the zipped file because the Etcher knows how to unzip on the fly. And then if I have more than one device here, then I can select it, and I can see that this is a 15.93 gigabyte drive, so I'm pretty confident that I'm not going to overwrite my root partition. And Etcher is pretty good about that. Etcher doesn't give you the option for overwriting your main hard drive, whereas if you use DD, bad things can happen if you're not careful. And that's it. And you press flash, and it needs your root password. And so it's going to burn this image, and we'll let that go. It'll tell you its percentage, and then it'll do a verification run. It'll verify the image. So I'm going to move this to my workspace over here, and we'll come back and see it a little while later. I think my recollection is it takes 15 minutes to burn the whole 8 gigabyte image, something like that. Not too long. If you're burning from Etcher runs under Mac and Mac OS and Windows, and students have experienced some bugs with Etcher where it computes the size of the destination device incorrectly. And so if you get some wacky, like not enough space to install, then you might want to try burning from Linux rather than from some other place. So these are the instructions that we just did. Once you burn it, then you want to gently install the microSD card, and so the microSD slot is right here, right in front of my finger, and right next to the micro USB slot. And what may not be obvious is this slides in with the connectors on the microSD card pointing outboard, away from the motherboard, not towards the motherboard. And so it goes like this. So these contacts are pointing away from the board itself, and then you just want to go in square and use a very light touch, and it clicks in like a Bic pen. Click one in and then one back out, one in and one back out. If you're doing this with the BeagleBone Black, it's a little tighter, and it's on the bottom rather than the top. So there's the card right here on the bottom, and what I do is we're powered up here. Okay, so just powering down so I can show you. So what I do when I want to get this, card out is I pop it out with one click, but it doesn't want to fall out. And so I use a pair of tweezers just to reach in there and grab the card and to pull it gently out. And then when I want to put it back in, I put a pair of tweezers to actually place it in the slot and get it oriented, and then I push it down with my fingers. Your fingers, I've got big, clumsy fingers, so your fingers may be small and able to maneuver in there just fine. But that's where it is. And also, and on this one also, the connector, the gold-plated contacts face away from the board. Okay. So we've inserted the micro USB image into the machine, and we'll boot it by plugging in the power, and the thing will boot up. And I'm going to connect the USB to my computer. These images, I removed Apache, so Apache doesn't run automatically, but they do DHCP serve. And they take a minute to come up. Watch -N1 will run that command once a second, and so once this comes up and it starts serving Ethernet over USB, we'll see additional entries appear here. That's weird. Every once in a while, something goes wonky with these things, and it doesn't. So there we go. Just took a while. So it's serving on two different addresses, 192.168.7.1 and 6.1, and so we can SSH to .2 of any of those. So .7.2. Yes. So we're going to log in as Ubuntu, and the password is temp password. Yep, Ubuntu. So we're in. There's the message of the day, just a little information on how this image came to be. So we're logged in, and then we want to test, see how our burning is doing. The burning is 49% done. And then we're going to run some tests here. Just follow the instructions. You're going to want to do, you can run the RC balance program. So RC balance. And it'll balance even though it's got a USB cable attached to it. Doesn't mind. And it will probably give you some error message. You can test encoders, RC test encoders. And so when I rotate the wheels, yay, my middle two encoders, increment and decrement. And you can test the motors. So RC test motors, minus D is duty cycle, and duty cycle varies between -1 and +1. So this will give a 10% duty cycle to the PWM output. So I'm going to flip this thing upside down so the wheels are in the air. And RC test motors minus D 0.1, and my wheels are rotating. And if I do minus D1, they'll rotate fast. And RC, we want to calibrate the gyro, RC calibrate gyro, and it's just going to collect some data for the offset data for the sensors, for sensor bias. And what it's doing is it just created a calibration file that lives in var lib robotics cape with the gyro offsets. And if you want to calibrate the magnetic compass, which I've already done on my machine, you do RC calibrate magnetometer. And what you do is you put that and you spin the robot around and around and around, and it calculates the sensor bias for the magnetometer. It knows that magnetic field vector has to be a certain magnitude, and that field vector will lie on the surface of a sphere, and it calculates scale and offset factors, and it creates the file var lib robotics cape mag.cal. And so you can test the magnetometers, you can test the gyros, RC test gyros. test IMU. I always get that wrong. And you can see it reads out accelerations, angular rates, and magnetic field and temperature. So you can see the acceleration is all along one axis here, and it's all along another axis there. And as I move it around, you can see the gyro seeing the angular rates. So just fool around with it, and you verify that the hardware all works. I like HTOP, and you can see that this system has half a gig of RAM and a 1 gigabyte swap space, DF minus H, and we've got lots of disk space available. There's 2 gigs of available space on this memory thing, and we can expand. That's an 8 gigabyte partition, and we could actually expand that to, if you need more space, we can expand it to use the entire microSD card. And so pre-installed on your system, this is the root directory, is opt ROS Kinetic. So ROS Kinetic is installed, and and there's a workspace, the Catkin workspace. Catkin workspace, build, devel, source, Catkin, make, and the usual things happen. So we're running out of time. So I don't have a whole lot more to do here to get you finished, but I like to be respectful of people's time. It's going to take more than 5 minutes to finish up. The thing that we'll finish next time is running I've provided 2 packages which you can pull down in the Catkin workspace source directory. There's edge-emit messages, which defines a custom message type for the edge-emit, and there's a program which is a ROS node which does the balancing, and it subscribes to a twist message, and you send it a twist command, and it'll drive with the velocity proportional to the twist, and it publishes a customized edge-emit state message. So that's preloaded, and you'll be able to do things like ROS core immediately. ROS core will come right up, and what we'll do next time is we'll finish testing this, and then we'll get back to the main thing. You've finished assembly here, and we're going to plug in a joystick, and you're going to write a ROS node which takes the joystick message and publishes a twist message, and then we're going to learn about running ROS across multiple machines. So we're going to have ROS core running on your PC and the joystick stuff running on your PC. It's going to be publishing a topic that the edge-emit ROS balance program is subscribing to that's running here, and this is going to be publishing state information that you can monitor on either node. And so you can do ROS topic list, and anything that you can do on one machine, you can do on another machine, and they'll be referring to a common ROS core. And that'll all probably take about 20 minutes next time, and then the rest of class next time you'll be able to hack. And we'll have a soldering iron here if you want to do some soldering too. So, any questions? All right, so it's a big assignment this week, but it's not a hard one, and hopefully it'll be a really interesting one, and I hope it'll be a good experience for you. All right, thanks everybody. I'll see you Thursday.